We all get pretty comfortable in our world. You throw a ball, you know exactly where it's going to go. It's predictable, it makes sense, that's classical physics. But what if you shrink down, way, way down, to the size of a single atom? Well, that's when the universe stops playing by the rules we know and starts a whole new game. A much, much weirder game. Welcome to quantum physics.
So, yeah, it's like we've got two different rule books for reality. You've got classical physics for all the big stuff we see, cars, planets, you name it. And then there's quantum physics, which runs the show for the tiny building blocks of, well, literally everything. And this is where it gets really strange, because down at that level, particles just don't act like anything we're used to.
I mean, you might be thinking, okay, so what? An electron's just a tiny little ball, right? Kind of like a miniature planet zipping around. That seems logical. Well, it's not quite that simple. And the answer to that one question opens up one of the biggest, most profound mysteries of the entire universe. To really see what I'm talking about, we have to look at what I like to call nature's greatest magic trick. This is the one, the famous double-slit experiment. And trust me, it is designed to completely shatter everything you think you know about how reality works. Okay, so the setup is pretty simple. Imagine you're shooting electrons, just one after another, at a wall that has two little slits in it. Logically, you'd expect to see two simple lines on the detector screen behind the wall, right? One line for each slit. Makes sense. But that is not what happens. Not even close. Instead, you get this bizarre interference pattern, exactly like you'd see if a wave had passed through both slits at once. Now just let that sink in for a second. The only way to get that wave pattern is if that single electron somehow went through both slits at the same time and then interfered with itself. I know, it sounds completely impossible. How can one thing be in two places at once? But wait, it gets even weirder.
This is the absolute wildest part. So, scientists, being scientists, said, okay, let's peek. Let's put a tiny detector by the slits to see which one the electron actually goes through. And the moment they did that, the very instant they looked, the wave pattern completely disappeared. Just gone. And the electrons started acting like normal little balls again, making just two simple lines.
This quote just nails it. The simple act of measuring, of just looking at the quantum world, fundamentally changes what happens. It's almost like reality is a little bit shy, and it waits for us to look away before it does its weird stuff.
So this isn't just chaos. It's not just random weirdness for the sake of it. This behavior is actually governed by a completely new set of rules. And these are rules based not on certainty, but on pure probability and a deep, fundamental uncertainty.
So, rule number one is something called the wave function. The idea is that before you measure it, a particle like an electron doesn't really have a specific location. It's not here or there. It's more like a ghost, a cloud of all the places it could be. It only picks a spot when we force its hand by looking at it. Here's a tastier way to think about it. Imagine you're baking a cookie. Before you open that oven door to check on it, that cookie is in a state of all possibilities at once. It's perfectly baked, a little burnt, and still raw all at the same time. The moment you open the door, the moment you measure it, that cloud of possibilities collapses, and it becomes just one definite cookie. And you just hope it's the perfectly baked one. And the next rule is just as trippy. It's the famous uncertainty principle. And what it says is that there's a hard limit to what we can ever know about a particle. You can find out exactly where it is, or you can find out exactly how fast it's going, but you can never know both at the same time. And this isn't because our instruments aren't good enough. The universe itself has a "you shall not pass" rule on that information. Now, as you can probably guess, not everyone was thrilled about this new picture of a fuzzy, uncertain reality. In fact, this idea of randomness at the heart of everything sparked one of the biggest debates in science history, led by one very, very famous physicist who absolutely hated the idea. And that physicist was, of course, Albert Einstein. He just could not accept that the universe was fundamentally based on chance. To him, it felt incomplete. He was sure there had to be some deeper, hidden rules we just hadn't found yet. He famously said, "God does not play dice." But here's the thing. For all of Einstein's incredible genius, he was probably wrong on this one. For the last century, every single experiment we've thrown at quantum mechanics has just confirmed how right it is. It seems the universe actually loves to play dice. And maybe the most mind-blowing proof is something called quantum entanglement. You can link two particles so that they're basically one system, even when they're far apart.
So if you measure one, you instantly know the state of the other, even if it's on the other side of the galaxy. Einstein called it spooky action at a distance because that's what it is, and yet it's real. Okay, so the quantum world is weird. Deeply, fundamentally weird. I get it. But you're probably asking, why does any of this matter for me? Well, believe it or not, this weirdness is the bedrock of our entire modern wired world.
That smartphone in your hand, the computer you're on right now, they're powered by millions of tiny transistors that only work because of quantum mechanics. They rely on particles doing the impossible and tunneling through barriers they shouldn't be able to cross. Lasers, hospital MRIs, the GPS satellites that guide you, none of it would exist without these bizarre rules. We literally tamed the weirdness to build our world.
And guess what? We're not done. We're taking these same unbelievable principles, like a particle being in many places at once, and we're using them to build the next technological revolution, quantum computers. Machines so powerful they could solve problems we can't even dream of tackling today.
And for all its strangeness, it's so important to remember this. Quantum theory is the most successful, most precisely tested theory in the entire history of science. Its predictions match reality with an absolutely mind-boggling level of accuracy. It might sound crazy, but man, does it work.
So let's just zoom out for a second and take in the big picture. What is all this really telling us about reality itself? Because the implications, they go deep, and they challenge some of our most basic ideas about how the world is put together. Look, if your head is spinning a little bit, don't worry, you're in very good company. The legendary physicist Richard Feynman once said this, and he wasn't kidding. We can use the math, we can build the tech, but to really truly get it on a gut level, that's another story. And you know what? That's okay. It's a mystery we're all a part of.
What quantum mechanics really taught us is that the universe isn't some giant predictable clockwork machine like we used to think. Nope. At its most fundamental level, it's this shimmering, buzzing, vibrant field of potential and pure probability, just waiting for a reason to become real.
And so that's the final question I want to leave you with, to just chew on. Is the world around us, are we, really made of solid, definite things? Or are we all built on a foundation of something far more mysterious? A universe made entirely of possibilities?